high-performance client-side web applications.
Can you hear me? That's great, because we need to talk about the performance of web applications. And one type of application that requires quite a bit of performance is games. So anyone in here like games? Who likes games? Oh, great, everyone likes games, of course. So I'm going to test your knowledge a bit. So one of these images is from a 5-year-old PC game. The other one is from a far newer browser game. Now, which one do you think is the browser game? Is it this one? Show of hands. Right, a few people. Is it this one? Is it the browser game? Right. Yes, I think we have a majority for this one. And yeah, you can kind of tell. Because today, it's not really possible to get the sort of performance out of web apps that you need to do something like this. I was at this web developer conference. One of the other speakers, he was from a game development company. And he had some pretty interesting things to say about the hoops through which his company jumped in order to get the performance out of the browser that they need. And this is what he was saying. So we have to put all our data structures in unboxed double arrays to make the game fast enough. And when we add new features, we just keep adding more fields to the arrays, because we just can't keep track of what all the older fields do. So clearly, they were kind of desperate to get some performance out of the browser, and they weren't really getting it while keeping sane. So it's not just game developers that need more performance. So most applications could benefit from pushing more calculations onto the client. For instance, if you have an application that requires you to go mobile, maybe on a poor connection, then it stands to reason that you can get a lot of improvements in responsivity, in user experience in general, and in performance by pushing more calculations onto the client. And of course, as users, maybe we'd like to be able to compute over sensitive data without having to send it to a third party, which we might not trust. And of course, for the economical side, companies might be able to save a bit on their electricity bills by pushing more calculations to the users. Maybe that's a fair trade-off for a free web service, right? Now, unfortunately, writing high-performance web applications is a lot like this. It's a game called Snakes and Ladders. And for those of you who don't know, the idea of this game is that you go from the bottom left corner to the top right corner. And whenever you hit the bottom of a ladder, you can go up it and gain some ground. And whenever you hit the head of a snake, you go down. Writing high-performance web applications is a lot like this, except the ladders don't take you up. They also take you down. Because while JavaScript can be quite fast under the right circumstances, there are just so many performance pitfalls. So let's say that you're writing a function, you want it to be super fast because it's going to be in your super fancy game. Now you're chugging along down here, and all of a sudden, bam, performance pitfall snake. Now you're back down to square one, and yeah, you just lost the game, basically. And this, of course, becomes even worse with languages that are not JavaScript, but compiled down to it, because now you have even less control over when you hit these performance snakes. And as if I haven't painted a bleak enough picture yet, this also depends on which browser you're using. So let's say that you have an application that runs super fast on Chrome. Well, now you try to see, okay, does it work well for my Firefox users? No, it's super slow. So now you fix it to work well on Firefox. And yeah, this is not a dig on Mozilla. It could have been the other way around. I just happen to think that there maybe were more Google people in the audience than Mozilla people. So now you fix your app to be fast on Firefox, but now it's slow on Chrome instead. So this is a game of whack-a-mole that can also be quite hard to win. Now, so if there are any Mozilla people in the audience, you might be even more offended because you already fixed this. Does my clicker work? Right. With ASM.js. So what is this? Well, ASM.js is a subset of JavaScript. It's very, very low level. It has a one-to-one mapping to machine code, and it was introduced by Mozilla a few years back. And the idea here is that you write your whole application in a language such as C++. You compile it down to ASM.js, and if the browser correctly detects that this is what you're doing, now your application is going to be really fast. Now, since this is the Haskell Symposium, I don't think I need to explain to you why I don't want to write my whole application in C++. Instead, this is what I want to do. I want to have this work, right. I want to write my application in a functional language, Haskell preferably. I want to run it on pretty much any web browser, and I want to have it run super fast, even faster than the ones I showed before. And the way which I want to do this by is through a domain-specific language embedded in Haskell. And what do we need from such a language? Well, I don't want to write my whole application in this domain-specific language, so we need seamless integration with Haskell, so it can go back and forth. We need control of the generated code. The code should be fast. Preferably, it shouldn't even be possible to write slow code in this language. And since the performance snakes hide in different places in different browsers, we also need to be able to specialize our code to different environments. And so I sat down and thought about this for a bit. Then I devised a little language. And this language is called Applite. It's named after this piece of rock, because this rock and the language are quite similar. So the feldspar mineral, the Applite mineral contains a whole bunch of the mineral feldspar. And at Chalmers, we have another EDSL called feldspar, which Applite draws quite heavily upon. So both the Applite the language and Applite the rock contain a lot of feldspar. So I'm no geologist, so I don't know exactly what else goes into feldspar the rock, but I do know that feldspar the language brings quite a few improvements on its own in order to fulfill the properties that we saw on the previous slide. So another similarity. And last but not least, neither the rock nor the DSL requires you to modify your Haskell compiler in order to use it. So Applite is simply a Haskell library which you can use in some web targeting Haskell implementation, such as GHC.js or Haste. So I'm going to walk you through the language constructs. It's going to be very brief because this is a very simple language. It's a monadic, quite imperative language, which has arrays. You can create them, you can read them, you can write them. It's got mutable references. You can create them, read them, write them again. And we have loops. So we have these like for loops, we have also some while loops and so on, but they're not in this example.
You didn't want to write in C++.
Right. I just want to write the tiny, tiny bit in Pascal. Right. So now that we're past the boring stuff, let's get into why this is kind of cool. So we want a seamless integration. And as maybe you saw on the previous slide, if you were looking at all of it and not just the highlighted parts, is that we imported our Applite function under a Haskell type. And down here, we call it just like any other Haskell function in the IO monad. How can this be? Well, it's all due to this function called Applite, which is the main user interface to the language. And it does quite a lot of things, as illustrated by this flowchart. So it accepts as its input a function written in Applite. It adds some marshalling between Haskell and Applite types and data. Then we take this whole thingy, compile it into JavaScript, and dynamically load it and create a function object from that. Now we create a Haskell stub, which when called calls this function object, and we have a Haskell function that we can call just like any other. These types are a bit more flexible than you've seen previously, though. So if we take a look at this example, here we have this standard in and from to function. It accepts two integers, a and b, and spits out the array containing all the numbers between a and b. So this function quite obviously contains effects. So we create an array, and we mutate it all over the place, and then we spit it out. But we can't really observe these effects from the outside. So ideally, we'd like to be able to import this function purely. Can we do that? Of course we can. We just leave out the IO part of the type. And now how is this possible? Well, notice that the only effects available in Applite are modifying mutable things, arrays and references. Now, since there are no arrays or references passed in here, we just pass an array out, there is no way to observe this mutation from the outside. And hence, we can import this function purely. Now, if we try to do this with this matrix multiplication function I used previously, we'll get a type error, because here we have arrays in the types. So any mutation to them could be observed from the outside. Applite also supports multiple backends, but unlike the usual case for multiple backends where you target different platforms, these two actually target the same platform. And why is this? Well, as I told you, the performance snakes hide in different places. And also it turns out that different use cases have different performance snakes on their own. Who would have thought? So we have one backend that spits out ASM.js code, this super fast thing under the right circumstances. It's very good for computing intensive workloads. Not so good for memory-intensive workloads. And if you want to know why, you should read the paper. There's also a plain JavaScript backend, which is a bit slower than the ASM.js one usually, but it's very good for the memory-intensive workloads. And of course, since the language is as restricted as it is, this backend also avoids all of these performance snakes. So you're guaranteed to get good performance either way. Now, my favorite part of Applite is that this whole compiler machinery runs in the browser. And why is this cool? Well, we can get lazy compilation. If you have a function that you're not using, we don't waste the cycle to compile it. It just sits around. It also fulfills this property that we want to be able to specialize over user input. So a Haskell host program can take some user input, or it can inspect your screen resolution, or the version of your browser, or the time of day, or the phase of the moon, all the stuff you need in order to properly optimize for the current situation. And then produce the appropriate Applite program, compile it, and run it, and hopefully have that be very fast. We can also recompile the programs as needed, which might seem a bit useless at first. Why would we want to compile the program more than once? We already compiled it. No need to waste more cycles. Well, even though multiple backends and these specialization capabilities lets developers experiment and try different things in different browsers with different workloads, the developer might not want to do that. The developer might be busy actually producing code rather than fiddling with 15 different browser versions. So in order to help this very busy developer, Applite automates part of this task. So let's assume that you have an application consisting of a Haskell host program and some Applite functions. Now we start by compiling these Applite functions. We don't care what browser we use, what specialization or anything. We just like compile it. We just want something that runs. Now, after a while, the Haskell program might decide that, no, I think that this function is running too slow. And then it can call upon the Applite backend specializer. And what is this? Well, this is a function which accepts as its input a previously compiled Applite function and a user-provided benchmarking function. And this benchmarking function is intended to be representative of the expected input for this compiled Applite function. Now, after receiving these things and being invoked, the backend specializer, for each available backend and combination of compiler settings, will go through these backends and settings, recompile the program, run the benchmarking function using this newly compiled program, and time it. Now, after all this is done, hopefully, one of the recompiled variant will have emerged just faster than the others. So when this happens, the specializer simply overwrites the previously compiled function with the new fast one, and the next time it's called, we'll get the new, faster, shinier version. So this might all be a bit abstract, so I'm going to show you this in action. So these slides, it's just a JavaScript, a Haskell program running in the browser with some parts written in Applite, like this implementation of Perlin noise, for instance. So it runs at 22, 21 FPS. I guess that's okay-ish, but I see some stuttering. I don't like stuttering. Let's invoke the backend specializer by pressing the magic button. And now, it's faster, 50% faster even. I think that's pretty nice for just pushing a button. Now, apart from these cool features, we also get some nice performance benefits. So we have this benchmark suite. I was going to show you some nice charts here, but I realized that when doing a dry run of this, I couldn't read the charts from 2 pages on my own laptop screen, so there's no way you would have been able to read them here. So this is a summary. For the benchmarks that we also wrote in Haskell, we saw a speed up of up to 2 orders of magnitude over the Haskell programs which we used the Haze compiler to compile. More interestingly, when compared to hand-rolled JavaScript, we saw a speed up of up to 1 order of magnitude. And the best part of all is that no benchmark was ever slower than the hand-rolled JavaScript version. So in fact, all benchmarks were slightly faster or much faster or super much faster than the hand-rolled JavaScript versions, which is kind of nice because that means that you're not really taking a performance risk by using this. For the future, as Phil pointed out, we don't want to write our programs in C++. So what we want to do is to implement a front-end language on top of this, because this is what we've been doing in Feldspar proper so far to great effect. It gives us some nice fusion and other benefits. We also want to parallelize this thing, and since parallelism in the browser is quite a hairy beast, I think this is could be quite an interesting crack. And probably the most fun crack is to investigate what can we do with hybrid backends. So normally, hybrid backends don't make sense. Either you have an x86 backend, or you have a Spark backend, or you have a JavaScript backend, or what have you. So it doesn't make sense to mix them. But these backends target the same system. What if we could identify pieces of applet functions that are likely to run better with ASM.js, pieces that are likely to run better with a plain JS backend, and then somehow mix these together? So I think that's a pretty interesting line of research to pursue. And if there are 3 things I want you to take away from this talk, is that you should use EDSLs to make your web applications, and other applications as well for that matter, faster. Because it's super easy to mix and match Haskell and EDSL code. And you can also get this cool specialization for free. So you don't really pay much, but you stand to gain quite a lot. Thank you.
Okay, now we have time for a few questions. There, Leonard.
Have you tried targeting WebAssembly yet?
No, not yet. I actually have a master's student working on something a lot like that.
Matthias here. How big is the... Oh, here.
Right.
You said the compiler lives in the browser. How much of a download is it each time? Or like... Maybe.
Sorry, how much?
You said the compiler lives in the browser. How
Yes.
big is that? How much does it enlarge my page?
The overhead?
Yeah, the overhead, like just in terms of getting it over the network.
Right. So adding the compiler in adds about roughly 100 to 150 kilobytes of unoptimized, unminified JavaScript.
Oh, it's not like including GHC or something?
No, it's not including GHC. So this is not a Haskell compiler that's included. It's just the applet compiler.
Mm-hmm. Cool.
Any other questions? Actually, I had a question. So you know how users always want more stuff? What are the chances of getting some of that to interact with a server? We're going to learn how to write a really efficient server in Haskell in a minute. Any chance that we can interact with Haskell running on the server?
Yes, absolutely. You should read my 2014 Haskell Symposium paper for information about that. And you should also stay tuned for next year when I hope to present something quite along the lines that you propose. So stay tuned, but for now it's a secret to keep you all interested.
Okay, thank you very much.
Thank you.
Okay, thanks.